Today, I want to talk about welding and heat affected zones and why welding is not maybe the best way to approach designing a suppressor. Now, I was a welding engineer out of the aerospace industry, okay? And one of the benefits of welding, if you're going to weld something together, is that it's cheap and that it's flexible. You can weld dissimilar materials together, and also the ease of manufacturing. It's very easy to manufacture because you make very simple fixtures, okay, or even complex ones that are relatively easy and cheap to make out of aluminum that hold the basically the items into location, and you can weld those. Now, the cons of welding, where welding does not shine, is the heat affected zone is the weakest part, so we got to pay attention to how the heat affected zone is going to work in real life in its designed environment. Cyclical loading, welds don't like cyclical loading, okay? Thermal cycling, welds don't like thermal cycling. So when we were doing fluidic connectors in the aerospace industry, so all of the oil, the hydraulic, the gas, the airlines for engine systems, and these engine systems are circular. They have nooks and crannies all around them, and there's complex 3D bent tubes all the way around. We had fittings that were welded to those tubings. Now that would be titanium, it would be stainless steel, it would be, we would even do aluminum, but aluminum would not be used on anything that had a pilot in it. So whenever I did the system for the Boeing UCAV, the Unmanned Combat Aerial Vehicle, we used aluminum fittings in that case because aluminum has a lot larger chance of failing, right? So they didn't design, because there was no human life associated with that drone, you would use a aluminum because it's a lot cheaper and easier to work with. So just to go over to some of the pros and cons of billet, like say if we weren't going to like weld a assembly together, and you're going to machine all that as one piece, the thing is it's strong, it's stable, and it's very predictable. Under cyclical loading, under heat treatment, like varying heat treatment or thermal cycling, it will perform exactly how we think it will perform. Okay, so that's very, very important to us because we can do things like shrink the cross-sectional areas and make it lighter to the point where we have a 2x safety factor, and we know we can shrink it down to this minimum material that's there, keeping it all together, and that will produce the expected result. It will operate and perform in the anticipated way under its conditions of how it's going to be used in real life. The problem with billet materials, billet strategy, is that it's expensive. It's slow for manufacturing and complex for manufacturing. You're removing a whole lot of material. You're taking it from one piece. You're not doing things like getting something like tubing that has all the material removed and welding it to another piece that was very small and machined from, efficiently from one piece. You're having to remove all that material, making the tubing as you go. So that's what's really kind of the negatives for a billet strategy, is that it's expensive, it's slow to manufacture, and you just can't put out what you can when you're doing welding, right? All right, so the actual weld. You have the base material, you're going to have a filler material, which the filler material is always the strongest, right? The actual weld joint itself is the strongest part of the weld. It's never ever going to break. It's the hardest, okay? Now, the weakest part is the heat affected zone. It's the blending. It's the where those two materials blend, and it's the effect of when this was molten and this was solid, there's a different microstructure there, a different chemistry there, right? And that chemistry and those changing microstructures make this area outside of the weld the weakest point. That's where it will fail at. Okay, that's where we always know things are going to fail at. Now you can weld dissimilar materials together. This could be 304 stainless steel. This could be 316 stainless steel. And the American Welding Society, after decades and decades and decades, maybe even a century of experimentation and testing across all different industries, has decided that maybe 321 is the best filler material to use for these dissimilar metals. You can even weld things like Inconel and stainless steel together. And in that case, you might use an Inconel filler material of whatever, 715 or something like that, 625. But the American Welding Society will determine that already, and you just go with those best practices. Now, if you do have dissimilar metals, again, the weakest point, typically on the weaker side of the material, is the part that will fail. Okay, so even if you have something very, very hard and strong on one side, and something that is weaker on the other side, what's the use of that? Okay, what is the purpose? Because it's going to fail here anyway at the weaker side's heat affected zone. Well, you may be trying to do things like get wear resistance on this side. Okay, take a Stellite or an Inconel blast baffle. Okay, but the failure point is still there. Okay, it could be there on the design on this side over here. Okay, now what happens is you got changing metallurgy here and different crystalline structures. We have what we call a body-centered cubic and a face-centered cubic. Okay, and it's where the atoms are lining up and how they're oriented. Okay, now when you heat a material like a steel up that has carbon, so all your stainless steels, all your steels have carbon inside of them. Okay, they have different alloying elements that chromiums and nickels and things like that make them the difference between stainless steels and Inconels and such like that. Okay, but there's always going to be some part of carbon in it, and in the carbon steel, the more carbon you have inside of there, the stronger it is. And when you heat this thing up, if you change these crystalline structures, they will change from a body-centered to a face-centered cubic. Carbon can migrate on the inside of that face-centered, of the body-centered and face-centered cubic. The face-centered cubic can actually hold more carbon, and it's stronger at that point in time. However, whenever you cool it back down, it's going to change back to a body-centered cubic. So you have this changing going on. Okay. And this is in the base material, and it's here, and it's here. Okay, so it's everywhere, but it's doing things differently. All right, that variation, as a designer and as an engineer, if we want something to perform the exact same way, if we're trying to get something very precise, you don't want a whole lot of variation. If this is all one piece that's a billet material, it's going to perform the same way and be very predictable on how it's going to perform, and we can actually get a more accurate performing, precision, quality item out that we're manufacturing when it comes to that. Now, going back here to the face-centered cubic, as it cools, especially under rapid cooling, well, as it cools, it's going to go to a body-centered cubic, but if you cool that rapidly, and rapidly is relative, okay? But under rapid cooling, it's going to distort, and it'll distort this into a completely different shape. And that will be a body-centered tetragon. And that tetragon, basically, that's when you induce stress into a part. Now, when you thermal cycle that back up, you'll relieve that stress, but in order to do that, that material is going to move. Okay? So now if you're translating this, and it's only moving a slight bit, but over molecule over molecule over molecule down the length of, let's say, a suppressor, it can move to a different location. And if it moves to a different location, your shot is going to be different in a different location. Okay? Or it's going to open up group sizes. Okay? Basically, that's it. It's in a different location, right? But it can perform differently as it heats and as it cools. Okay? Now, take that heating and cooling under what's happening here with these body-centered and face-centered cubics, and it's not really a great idea. Okay. Also, when you're heat treating, you're basically heat treating. If you're going to take things up to, in the other video we said Cerakote fails at 1800 degrees. Well, these are tempering and these are hardening processes for heat treatment. Okay, so you're changing the state of that material as you're shooting the suppressor and then cooling it back down. Okay, so a losing welding strategy, if you're going to design any part out there, a strategy of what you choose to approach to deliver that product or manufacture that product and how it's going to perform reliability. We call that design for reliability, right? A losing strategy, or a one that's very hard to overcome, is going to be thermal cycling with welding. It's not a good idea. Or cyclical loading, where pressure is constantly going up and down. We welded in the aerospace industry fluidic connections together. Things that hold 5,000 psi of fuel lines. But it was constant state. It's not cyclical loading. Yeah, you load it up, but it's constant state. It stayed at 5,000 psi the whole entire time, pressurized in those fluidic assemblies. And that's where it stayed. That's not cyclical loading. So those applications were okay. Now, vibration was another thing. And in aerospace industry, we were concerned with the next factor, which was vibration. We don't have a lot of vibration inside of the suppressor industry, right, other than barrel harmonics. But vibration was one that's not as affected, doesn't affect the heat affected zones. We considered it. We made sure that it was taken care of. Okay. But you can get by it. Now, thermal cycling, even in the aerospace industry, you're going up to way up high in altitude where it can be freezing, very, very cold, and then back down to Afghanistan where it can be super, super hot. But we're talking about relatively heat here, right? So 1800 degrees heat is totally different than 400 degrees heat. Okay, and a lot of times things in aircrafts are not going to work well at 400 degrees either. You're going to say, like all engines, you have a cooling system in the engine and you max out at like 210 degrees. That's elevated temperatures. So whenever you hear that a material performs well at elevated temperatures, that could be between 200 and 400 degrees. In suppressors, we're talking about superheated elevated temperatures. Okay, so there's a scale, a relative scale here. Okay, so don't be confused by marketing stuff where it says, oh, well, you know, and you can actually go look it up and search on the internet that this stainless steel, 321 stainless steel is better at elevated temperatures versus this other material. Well, yes, it is at 300 degrees. But how does that perform at 1800 degrees, the point at which Cerakote fails? Because we fail Cerakote all the time. So it's relative, okay? But a losing welding strategy in general is thermal cycling or cyclical loading. Now we're combining those together with suppressors. You're going to do thermal cycling and cyclical loading all combined at the same time, okay? Now, how do you overcome it? If that's a problem, you can overcome it. And the way you do that is by large cross-sectional areas. And when you do large cross-sectional areas, you basically are going to beef up this weld joint. Okay? So now your area, your cross-sectional area is much larger. And your weld joint's much larger, but you increase weight. So welded cans need to be heavy. Okay? They're overcoming these problems. They're overcoming them all. But they have to be heavy in order to stay reliable and not shoot off the end of the gun. And yet sometimes they still do. The reason that they still do is because maybe on that suppressor, okay, that individual serial number, there was a welding defect, okay? Okay, so some of these welding defects could be something like this, okay? Or undercut, right? Where it's like this, okay? And at each one of these points under cyclical loading, there is a stress point right there. There's induced stress, and that's where cracks can propagate from. And that's just the quality of the weld, and you actually have to have a certified welding inspector to inspect for those defects. And not all the time they can be caught. Sometimes they're in that gray area where it's passable, not passable, and a lot of times they're fine. But other times it's not. there's a lot of factors going on, because maybe that the temperature of that weld joint, whenever it was actually welded with the combination of that, those things work together to form to propagate a crack, and that crack propagates through and it goes. And those are just things that come along with welding. It doesn't mean that that manufacturer is a bad manufacturer. They could be one of the tops. The thing is that you're always going to have chances of error in manufacturing systems. You always do. Even Toyotas that are produced all have, there's a quality defect that makes it through the system, okay? Because it's very hard to identify those quality defects. It does not reflect on that manufacturing at all, okay? The thing is, you're going to have a failure rate. You produce 1,000 suppressors, how many fail? Okay, 1% failure rate, which is pretty freaking low. It's pretty low. It's 10 cans. Okay, so that manufacturer produces 1,000 suppressors. You're gonna have 1,000 happy customers with that, or you're gonna have 990 happy customers with that suppressor company, and 10 people are blasting that company because of failures. Okay, it's not that the company is bad. It's not that even the design is bad. It just is life. It is manufacturing. You get, that's a 1% failure rate, which is not horrible. It's not great. It's not horrible. But the thing is, if you're doing 10,000 suppressors in a month, now you have 100 occurrences. Now 0.1% would still be 10 on 10,000 suppressors. Okay, and you're going to hear all about those 10 online. And that's going to form an impression in your brain that that suppressor company is horrible and they have all these problems, when actually it's really not, because they have so many happy customers. And as long as they take care of their customer, as long as they fix the problem, it should not be an issue, because you're getting taken care of. You're going to get a quality product. And I really have this to say about the suppressor industry, is that on the whole, all the suppressor companies that are in existence today are taking care of their customers. That's just it. They're all doing a great job for all of us out there, and that's a good thing for the industry. Okay, so don't worry about the failures. Don't worry about this. This discussion is about why are welded cans maybe not the best strategy to use, and we're able to relate heavy with welded cans, and that's reliable. They're built like tanks. Okay, they have to be. All right, that pretty much covers it for what I want to go over today. When you're able to do the billet strategy, when you're able to machine it, so monocores. Now, when you weld that monocore up to everything, then you've got welds again. Okay, but let's just say a 22 can is threaded together a lot of times, and they're monocores, and they perform exactly how they're intended to perform. You're not going to have those failures. Not only that, it can be light, because we know exactly how that material is going to perform, and we don't have to guess about how some heat affected zone and all this variation here that's changing under thermal cycling and under cyclical loading, and over time of use of that suppressor. We don't have those worries with billet type manufacturing processes, right? With that strategy. The problem is that it's expensive. Okay, it's very expensive, because you have to buy so much material. And imagine titanium. You're buying so much titanium, and you're just machining away all that material. There's no ways to reduce that cost. Then you're also machining away all that material. It's slow. And then it's complex, because if you have features in there, welding, you can get complex angles and all that stuff, and set that up pretty easily, zap it, weld it together, and you're good to go. But in manufacturing billet strategies, you have to design complex materials, have very expensive machines, maybe fourth axis, such things like that. And it's going to be very, very, very expensive business model. Not only is it the materials, but you got to have much higher skilled people. You got to have programmers that are much more skilled. You got to have fixtures that don't cost you $500 to make. They cost you $5,000 to make. And then it's going to be slow. Okay, so this is a battle that you're going to fight with the billet basically approaches of maybe those companies are slower to deliver than the welded can companies do, okay? And they're going to be more expensive, okay, than the welded can companies, because that's just the nature of the beast. However, they might be more predictable because it's just a strategy. When Mother Nature is working with you, instead of trying to overcome Mother Nature is going to slap you down every single time. Okay, we are not smart enough, people in general. Take the smartest person in the world, the biggest expert in the world, is still going to be learning things about nature and about welding and about microstructures, and there's still going to be an occurrence for failure. But if you stay away from that as a welding engineer, what the things about welding processes, the chemical processing that's required prior to welding the stuff, prepping it right, is an EPA nightmare. It's very expensive for that process as well, especially titanium. It's not that way set as much for, say, your stainless steels or your aluminums, right? And if you have multiple different materials that you're working with, you have to have different processing. Now, in some cases, these companies choose not to do the chemical processing, the acid pickling, the etching, all of these things prior to welding that we did in the aerospace industry, okay, which makes it even cheaper, it makes it even faster, but it's more prone to failure if you don't do it the correct way. We like to do things here the correct way, and I've identified that welding titanium the correct way would make a can a lot more expensive and more prone to failure. So we went away from that, and we machine out of billet, one-piece billet material, our monocores, and there are no welds whatsoever. Now, they're not disassemblable. You can't take them apart and clean them, because we also assemble them in a way that they're more permanently assembled. We can service them, but you're not going to get them apart. There's no use in doing that on a rifle platform anyway, because you know, it's thousands upon thousands upon thousands of rounds, and the carbon actually does things to like cement everything together. It actually is going to deaden some of the tones and stuff like that inside the can anyway. We want some carbon inside of there. We want it to carbon up a little bit. Now, in excess, there's things that you can do, like dropping it in hydrogen peroxide. Do not do vinegar in that. Vinegar, if you have any melanite components like brakes or something like that, you'll actually strip the melaniting QPQ off of those components if you put them in vinegar. And then your brakes are going to rust, they're going to lose their hardness, they're going to do, it's going to be just not good. Hydrogen peroxide, drop it in there until it stops fizzing. Only do that once. Don't over clean things, okay? You're going to cause problems if you over clean them. So that's all I got to talk about today for welding your cans. Get with us today. It's the best time to buy suppressors. It really is. The wait times are super short right now, the shortest we've seen in a long time, and it's just a good time. The technology is at its best. We offer cans that go across everything from pistols to every single platform up to 408 Chi-Tech right now, all the way down to 22 long rifle, with our axes and our Saxons that are really, really freaking quiet. So we are going to be some of the quietest. As we always are going to talk to you on the phone. We're going to say, hey, we might not be the quietest suppressor out there, but we are going to be the lightest and the most accurate. Okay? But what we're hearing right now when we're going head to head and competing against others is that we're knocking the socks off of people in the quiet space as well. So give us a call today. We'll take care of you. And the benefits of our suppressors are something that you can pass down. And not only just the suppressor, but you're passing down the knowledge of shooting. You're passing down the experience. You're passing your legacy on. Because at the end of the day, no one's going to ever remember how much money you made. They're just not. They won't remember you for a lot of your accomplishments that that you made, but they will remember you for the time that you spent with them and how great of a man you were and how you invested in them and how you made them feel. Okay, that's what leaving a legacy is all about. So, get your can today, get it processed, get it approved, get it in your hands, and go shooting with someone. That's all we got today. Pro Suppressors, your legacy performance.